Hello, we can continue with the next IB exam question. As you see here, we have a function f, a real function that's differentiable for each value of x, and f of x plus y equals f of x times f of y. And f of 0 is different than 0, then I have to prove that f of 0 equals 1 and some other sub-questions. So I'm starting with the first part, and I'm going to prove that f of 0 is 1. Since from the statement of the question I have f of x plus y equals f of x times f of y, for each couple of x and y, I can take any number in the place of x and any number in the place of y. So I'm starting with x equals 0 and y equals 0. Substituting here and here, we have that f of 0 plus 0 equals f of 0 times f of 0. From here, f of 0 equals f squared of 0, so f squared of 0 minus f of 0 equals 0. So f of 0, I have a common factor here, times f of 0 minus 1 equals 0. Now, since this product here is 0, f of 0 is 0, or f of 0 is 1. But my hypothesis stated that f of 0 is different than 0, so it's impossible, and this case here is rejected, so I accept that f of 0 equals to 1. But that's what I wanted to prove in the first place. Now, I continue with part B. I have to prove that f of x is different than 0 for each value of x. Now, we will give a proof by contradiction. When you give a proof by contradiction, you have some hypothesis, and then you have some conclusion that's false. So I create a hypothesis and the conclusion is false. So since my conclusion is false, then I have to reject the hypothesis. So that's the structure of my answer here. And since I want to prove that f of x is different than 0 everywhere, I will take the negation of this proposition here. And what's the negative proposition of f of x is different of 0 everywhere? That there exists some number a real number, such that f of a is 0. So that's my hypothesis, and you can imagine that since a is a number, I don't know if this number is positive or negative. Suppose it's less than 0, but I could think as well that the number is more than 0. This number actually couldn't be 0 since f of 0 is 1, so definitely a is different than 0. Okay, now if we take f of a plus minus a, so in the relation f of x plus y equals f of x times f of y, I substitute x equals a and y equals minus a. So I have f of a plus minus a equals f of a times f of minus a. Now, a plus minus a is 0, so f of 0 equals f of a times f of minus a. Now, we know that f of 0 is 1. So we have the relation here 1 equals, but f of a is 0, so the second member of that equation is 0, so we have 1 equals 0, but that's false. So my hypothesis, this is my hypothesis, gave me a false conclusion. So my hypothesis is false. So there does not exist an a such that f of a equals to 0. So f of x is different than 0 for each value of x that belongs to the real numbers. Now, for the part C, I want actually to find the derivative at a random point x. So suppose that you get a random point x that belongs to the real numbers. So that's random, but I can suppose that it's fixed momentarily. I need that to be fixed. So I need the derivative of f at the point x, but that's the limit of f at x plus h minus f of x over h when h tends to 0. So you have to notice here that my variable is h and not x. I suppose that x is fixed. I want to find the derivative at the point x, at a fixed point x, and my variable is h. So from the statement of the question, f of x plus h equals to f of x times f of h. So minus f of x over h when h tends to 0. But this is the limit of, if I have here a common factor, this is f of x, so f of x times f of h minus 1 over h, where h tends to 0. This is constant because it doesn't include my variable h, so the constant can go out of the limit, and it is f of x times the limit of f of h minus 1, but don't forget that 1 is f of 0 over h when h tends to 0. Now if you take that expression here, easily you understand that this is the derivative at 0, because the derivative at 0 is f of x minus f of 0 over f of h minus f of 0 over h when you substitute 0 here. So this is f of x times derivative of f at 0. Yeah, but I have just proved that the derivative of x, the derivative of f at the point x equals to f of x times f derivative of 0. So if you say that this expression is k, it's a number k, then the derivative of f at x is k times f of x for each value of x that belongs to the real numbers. Now, the part D starts from here because I want to solve this differential equation. So the derivative of f at x equals to k times f of x. I separate the variables here, so I have f derivative of x over f of x equals k. So I have the integral of derivative of x over f of x dx equals the integral of k dx plus a constant c. From here I have the logarithm ln of f of x, that's this integral, so equals to kx plus c. Now, from the definition of the logarithm, I have that f of x equals to e to the power kx plus c. I don't need to have absolute values since I know that this expression here is always positive. So the last part is to find c. I need to evaluate the constant c. That's an IVP, the initial value problem, that I know that f of 0 equals to 1. So I substitute in that relation, I substitute x by 0 and f of x or y by 1. Then I have 1 equals e to the power c. If you solve that, you find that c equals to 0. Then I substitute c here, and my final form is that f of x equals to e to the power kx. Of course, k equals to the derivative of f at the point 0. It means that my solution when f is differentiable is actually the exponential function of the form e to the power kx. It was a good exam question for IB, and somebody should have the technical ability to use this definition of limit in a smart way.